Hello everyone. The second state FaaS is a high-performance function as a service. It has some very unique features. First, it is based on WebAssembly and is lightweight. Unlike other FaaS solutions, it does not need to spin up an operating system and then a runtime stack. That means the second state FaaS function cold starts in sub-milliseconds and runs very fast. Second, the second state ahead of time compiler enables its functions to run at native speed while preserving safety. Furthermore, the TensorFlow extensions of the second state VM allow AI and big data applications to take advantage of native hardware features, such as the GPU and AI inference chips. Third, the second state FaaS is one of the first serverless offerings that fully supports Rust. Rust is one of the most beloved programming languages by developers. It enables you to write high-performance, yet memory-safe functions. In this video, I will show you how to create a high-performance face detection function. On fast edge networks with specialized hardware, it could provide real-time face detection in video streams. But even under average Wi-Fi networks, it is sufficient to detect faces from a continuous stream of photos from door cameras or other monitors. First, let's look into the Rust function to detect faces. The function takes a byte array as input. The input is the raw data of a photo. It returns a byte array. The return value is an image with the faces marked by hollow squares. The function first loads a face detection TensorFlow model. The model is already trained on thousands of faces. Here we choose the MTCNN model. The function also specifies how to configure the model parameters, such as the minimal sized face to detect. The function loads the image data and flattens the image into RGB data. This type of data preparation is the bulk of the work in Edge AI functions. The function then calls a TensorFlow command to run the model against the image data. Notice that the function passes to the command the TensorFlow model, as well as the input and output tensor names for the model. That allows developers to use the same command for many different models. Once the model execution completes, the function reads the result. The result is a series of number coordinates for the detected faces in the image. The function now draws boxes around the faces in the original image and then writes the output image. Again, this type of post-data processing is time-consuming and must run in a high-performance runtime, like the second state FaaS. Next, we compile and build this Rust function into WebAssembly bytecode using the SSVM-up toolchain we provide. Now we can upload and deploy this WebAssembly function, which already included the TensorFlow model itself, to the FaaS service. Notice the WASM ID in the return? That is what you need to call this function later. Next, we have created a static HTML web page that uses JavaScript to invoke the remote function. We do not build any servers. Serverless all the way. We add the WASM ID in JavaScript and load the page. Now we can pass in an image URL from the web and see all the faces outlined in boxes. This is a photo of the 1927 Solvay conference. Of the 29 faces, 17 of them won the Nobel Prize in subsequent years. Can you recognize some of them?